Hi, so we're going to chapter 11, which is about thermal energy, heat, and work, and is much more applicable to our daily lives and much more obvious than the past few sections have been, especially the special relativity and general relativity sections. So the first thing that we want to talk about when we talk about heat and thermal energy is temperature. So the literal definition of temperature is the measurement on a thermometer. But when we look at different, when we look at it more closely and we take some mathematical leaps, then it turns out that the thermal energy of a material, which is the average kinetic energy of the molecules or atoms, is directly proportional, which means that it's directly lines up to the temperature of a material. So temperature is measured in Fahrenheit, Celsius, or Kelvin, where the the where the conversion between these different temperatures is given to the right, where and Fahrenheit is measured to have the freezing point of water at 32 degrees. Celsius is and the free boiling point of water is significantly higher in the hundreds of degrees. Celsius is measured to have the freezing point of water at exactly 0 degrees and the boiling point of water at exactly 100 degrees. And Kelvin is measured so that the kinetic energy of the atoms becomes zero at the point where the Kelvin scale becomes zero. So this is known as absolute zero, and it's actually impossible to get to absolute zero by experimentally or uh, in nature, but we've gotten within, I think, about 1,000th of absolute Kelvin uh, within absolute zero, and then 1 Kelvin within absolute zero in nature. So 1,000th of Kelvin in absolute within absolute zero in a lab, and 1 Kelvin of within absolute zero in nature, which is in the Boomerang Nebula, I believe. So the conversion between Kelvin and Celsius is just that the temperature in Kelvin is 273 times the temperature in Celsius. So when you raise a temperature by 1 Kelvin, you raise the temperature by 1 degree Celsius. So that's about how small of a difference we've gotten. We've gone within about 1/1000th or 1/100th. Uh, the exact numbers escaping me, within absolute zero uh, in a laboratory setting. So heat, when we talk about temperature, we usually talk about heat, but formally, scientifically, heat is not a measurement of temperature, but a transfer of energy from a hotter object to a colder object until both objects are at the same temperature, which is going to be measured in units of joules, just like you can convert between temperature, which is measured in Kelvin, and joules by finding the average kinetic energy for a temperature. You can uh, tell you're going to be measuring heat in terms of temperature, uh, in terms of joules, which is the terms of the energy that is transferred from one object to another. So the amount of heat that's transferred in a or sorry, the amount of heat that's transferred uh oh from one substance to another depends on the amount of a substance, the change in temperature, and a property of the material called the specific heat. So if something has twice as much of a temperature change, then it's going to release twice as much heat. If something has twice as much mass, it's going to release take twice as much heat to heat it up. And then if something has a higher specific heat, then it's going to take more heat to heat that material up. But so you don't always meet exactly in the middle when you place two objects that are different temperatures near each other, because the heat transferred from one of those objects, if you have like a really hot marble and you have the earth, then the mass of the earth is going to be so big that even though the amount of heat that's released by one object is equal to the amount of captured by the other, because the mass of the earth is so much bigger than the mass of the really hot marble, it's basically not going to cause any change of temperature of the earth, while it's going to cool down the marble almost exactly to the temperature that the earth was already at. So there are three major, or I think just three methods of transferring heat. So these are conduction, convection, and radiation. So a conduction is heat transfer through a direct physical contact and is dependent on how good a material is at transferring heat compared to other materials. So if you're walking along a carpeted floor, it's not very good at conduction. So you're not going to lose a lot of heat. But if you walk across a metal or a linoleum floor, then those are very good at conduction, and you're going to lose heat much faster than you would walking across the conducting or the carpeted floor. And then convection is heat transfer by the movements of a fluid. For example, air moving through a home. So the heat rising through a home, so the heat goes up to the rafters of the home and pushes colder air down. So that is an example of convection. And then what happens with a pot that's warming up is that the heat starts at the bottom and then builds, is transferred through a fluid. So a fluid is just something that's able to move its particles around readily. So it's like water or a liquid or a gas, which we're going to get into later. But the heat goes through the bottom of the pan through conduction, and then gets transferred to the fluid, where the heat is going to rearrange itself through the fluid through convection. And that's how you warm up the entire water pot, even though you're only transferring heat at the bottom of the pot. And then radiation is the only method of heat transfer where no medium is required, meaning that the heat doesn't need to come into direct contact with or be transported by any matter. So it doesn't need to be, it's not like conduction where you're touching one material to another, and it's not like convection where the fluids are touching each other and moving the heat around. It is just the transfer of radiation, which is generally light. So examples of this are fire, which mostly warms you up through ultraviolet radiation, or light from the sun, which goes through space. So it's obviously not touching anything. It's not moving any matter or causing heat to transfer between any matter, but it still manages to warm up the entire Earth. So the last thing that we need to note for this, and again, this is very applicable to your everyday life, is that sometimes adding heat doesn't change the temperature of a substance, and this occurs during phase changes and is called hidden or latent or hidden heat, where latent is just a word for the another word for the word hidden, and is given by the equation Q equals ml, which again, you're not expected to memorize, but tells us that there's some property of the material that that shows how much heat is going to take to cause a phase change. And the more material you have, the more mass that you have, the harder it's going to be to cause a phase change. So if you melt one ice cube, it's going to take significantly less heat than it takes to melt an iceberg. So a phase change is a change between phases of matter. So the phases of matter that you're probably familiar with are solid, liquid, and gas, where solid is something where the particles or the molecules or the atoms that make up the matter are tightly bound together by electromagnetic bonds, which we'll get into later. So they're tightly bound together and they cannot move other than very slightly vibrating or moving within their crystal structure. So the crystal structure is just how the molecules in solid are arranged, and they cannot move with regards to that structure. So they're stuck in that structure. And then the second phase of matter is liquid, where the molecules are allowed to move a little more, but they can't change their volume. So they can change their shape and fit into whatever container you put them in, which is something that solids can't do, but they cannot change the volume. They cannot change how much space is taken up by the material. And then the last common phase of matter that you're going to see in your everyday life is called gas, which is something where the electromagnetic bonds or the electricity and magnetism bonds that keep forces that keep the materials together, keep the atoms together, are pretty much completely non-used or completely non-factors. So they're able to move wherever they want. They can expand, they can take up as much space as the container they're in, and they don't have a fixed shape. So they have the shape of the container they're in, but they can also take up as much volume as the container they're in. And then the last, so that's the three common phases of matter, but you can also have plasma or other phases of matter which are more complicated or complex, where plasma is just something that where you get really, really hot and it ionizes the molecules so that they're charged particles instead of just being neutral particles. But that's not going to be really important for what we are doing. I'm not even sure if the book's going to get into ionization, but is something that's going to come up in a chemistry class if you ever take one of those. So these phase changes are changes from one state of matter to the other. So the phase changes from Less energetic to a more energetic state include the following: melting, which is solid to liquid; vaporization, which is liquid to gas; and sublimation, which is solid to gas. Whereas phase changes to a less energetic state are as follows: condensation from gas to liquid; freezing from liquid to solid. So, uh, when you input energy into breaking chemical bonds, then that's going to cause, or chemical or electromagnetic bonds, which are the bonds that are holding a solid into place, keeping a solid from moving around. So it's just forces keeping a solid from moving around that happen to be electromagnetic. So when you input energy, that's going to melt the material and cause it to become a liquid. But when you take away energy, it's going to cause the material to freeze. For liquids to gas, if you boil energy, if you input energy, then that causes the electromagnetic bonds, electromagnetic forces to weaken, which turns it into a gas. And if you take away energy, it causes it to condense into a liquid. And then the final example down here is just if you happen to be in the right place. Usually it goes from solid to liquid to gas. But if you happen to have the right pressure and temperature and all of the right conditions, then you can make it so that solid goes directly from solid to a gas, just completely skipping the liquid phase of the material. So that's about it. I hope that it was helpful and that you learned a lot about your everyday life from this. If you have any questions, again, just let me know and I'll be sure to try to answer them. Thank you very much. See you next lecture.